Okay. Well, first of all, thanks to the organizers for inviting me to speak, and also my apologies that I can't be there in person. Today, I'm going to first give you an overview of the research approach of my group, and I'm going to highlight in particular one direction which I'm very excited about, and that's how non-reciprocal interactions can give rise to collective dynamics and work generation. And this is that there's actually new faces to the story, so I'm going to try to focus on those aspects. Right. So I think broadly, we're interested in identifying self-organization principles in living systems across scales. And of course, one of the fundamental questions that we ask in physics is not only discovering the underlying laws in the system, but in understanding and explaining the new laws that emerge when many individual components interact. And to discover these laws, we do not always keep track of all the electrons and protons. We are always looking for important variables and key degrees of freedom. And once these variables are identified, we combine them into an order parameter, which is the quantification of the emergent phenomena. Now, this concept of order parameter in equilibrium physics, as we know, has been very powerful, and it plays a crucial role in defining a wide range of phenomena. Now, asking for the order parameters of the living state is, of course, not a well-defined question. And this is because when equilibrium is given, statistical mechanics frames the behavior and phenomena in terms of minimizing the energy, so since no energy is added or lost. But when a system is out of equilibrium by necessity, such as the case in living systems, we can no longer follow an energy optimization principle. So the question is, can we identify general principles that can guide us in developing a physics of self-organization in living systems that can reach the same level of predictive power that has been the standard in any other area of physics? And this is the challenge that we have set out to address under the umbrella of active matter. And to do so, we develop experimental tools to observe and identify non-equilibrium degrees of freedom. We develop data analysis frameworks to define order parameter fields. And lastly, we collaborate with my theory colleagues to develop theoretical frameworks with predictive power. Now, our ultimate goal is that the concepts that we introduce are system independent, both across different systems, but also across scales. But we always need model systems with rich phenomenology to be able to develop these type of frameworks. So I'm going to quote Rob Phillips in his famous, in his article celebrating Schrödinger, where he says that we need a hydrogen atom. And just like hydrogen atom was this quintessential test case for accounting for the behavior of atom all the way to Bose-Einstein condensate, I'm going to introduce you to the hydrogen atom, or actually the periodic table of this talk. And what you see here is a tiny branch of the phylogenetic tree. It's the echinoderm branch. And this slide, I'm showing you three of these species that belong to this branch. And echinoderms are this exceptional group that starts with bilaterally symmetric larvae that develops into pentameral adult symmetry. So for this talk, we'll be focusing on the embryos, which are, the way to think about them is that they are chiral self-propelled particles. They have a corkscrew swimming motion, and this is due to ciliary dynamics. So the main part of my talk is focusing on Pituria, our beloved starfish, and I'm going to talk about living chiral crystals. And then at the end, I'll show you one slide, if time permits, on sea urchin and the emergence of a p-adic active liquid crystal. And my hope is that to emphasize the fact that a combination of time reversal asymmetry, chiral asymmetry, and action-reaction asymmetry can give rise to emergent new phases of matter. Okay, so let me introduce you to the protagonist of my story. So this is a fertilized starfish oocyte where we have started the fertilization process. And what you can see is that we start from one egg cell, which undergoes the first symmetric cell division. This process continues many, many times. And since the focus of this meeting is tissue mechanics, you can imagine that there is a lot of cell migration and morphological changes are happening within this fertilization envelope. Now, at some point, we have a group of cells that are mostly migrate to the surface of this sphere. And these cells have cilia. Cilia is this hair-like protrusion that beats, and it's involved in swimming and developmental signaling. Now, these embryos are covered with cilia. At first, they beat asynchronously, and that's why you see this type of chaotic motion. But at some point, they start beating synchronously, and that's when these embryos start swimming. So there are two important symmetry breaking processes happen here. One is, of course, time reversal. This is development is happening, as well as chiral symmetry breaking. And I'm going to focus on chiral symmetry breaking for a little while. So this is a microscopic close-up of one of these embryos. And you can see that the embryo is, what's labeled here is a protein that labels cilia. And you can see that the embryo is covered with this, with cilia. And also you can notice that there is an axis of symmetry, which is called anterior posterior axis, or the AP axis. Now, as I mentioned, this ciliary beating pattern is involved in induction of left-right asymmetry in many organisms, including us, but also many other developmental signaling processes. Now, if you look at the red box here, we can look at a high-speed video of basically these ciliary dynamics. And you can see that we have a sparse ciliary carpet that's actively beating, and that's why these embryos are swimming. Okay, so now what we're going to do is we're going to look at a side view of one of these embryos. And just so we orient ourselves, what we are looking at is the water-air interface. And the bottom the bottom object that you see is the embryos that come to the water-air interface. And the top is the reflection of these embryos. Now, what you can see is that in individual embryos, they come to the interface with their AP axis perpendicular to the water-air interface. And you can see that they're stably spinning around this AP axis. But I also want you to note that sometimes they actually have a little bit of a tilt with respect to the normal vector. And this is something that I'm going to mention, and you will see it actually introduces a whole new phase to the dynamics of these systems. Okay, so we have these spinning objects. What can we do with them? We decided to put a large number of these embryos together, and we observed this absolutely remarkable phenomena. So in the first frame here, you see all these spheres, and note that each of these are an embryo, and we are looking from the top at the water-air interface. So I'm going to start the video. And what you see is this spontaneous crystallization of a large assembly of these developing starfish embryos. Over the course of their natural development, thousands of these swimming embryos come together to form what we call a living chiral crystal structure that can persist for many hours, days actually. And what you notice here is that they break global chiral symmetry. So they have actually a preferred global rotation. Now, the self-assembly dynamics and dissolution of these living chiral crystals are controlled entirely by the embryo's internal developmental program. So it's an entirely autonomous process. And again, I want you to note the scales here. This is a collective phenomena that's happening over days, and it's also on millimeter scale. So you can actually observe it by eye. And to just illustrate that, let me show you and also give you a sense of scale. This is a photo of these crystals taken with an iPhone camera. And what you see is there is a 6-well plate, if it means anything to you, but you can see this initial crystal formation. So you can see many enucleation events, and then they start merging, and then you get a large slab of this crystal. So I'm going to briefly give you an intuition about why this happens. So this is a side view of the embryo, and you can see the AP axis orientation. And what you can see again is that the embryo is slightly elongated along this axis of AP, in this axis of symmetry AP. And when the embryo swims to the water-air interface, as you saw in the video, they attain this stable configuration such that the AP axis is aligned perpendicular to the interface. Now, here you can see the fluid flow that's generated by one of these embryos. Now, a group of these embryos that align in this manner can spontaneously self-organize into two-dimensional hexagonal crystals. Now, as the embryo develops, what you can see is that both the shape as well as the topology of this self-generated fluid flow near the embryo's surface changes substantially, which leads to disassembly and eventually complete dissolution. Now, this radial inflow that's generated by this isolated embryos can be accurately captured by a Stokes slit singularity. This was shown by Alex Mitke, who's one of the locals there. And this is the fit both in our experiment and the theory. Now, this self-generated Stokes slit flow does two things. One is that it stabilizes the upright AP axis orientation of the embryo, but in addition, it induces an effective long-range hydrodynamic attraction between the embryos, which facilitates the assembly of long-lived clusters at the water-air interface. Now, as the starfish spins, they pull the fluids towards them and then downwards. And this fluid motion, of course, causes a reciprocal attractive force that leads to creation of this crystal. But the motion of the fluid also generates a second transverse force that actually cannot be ascribed to a potential energy. And this leads to emergence of unusual material properties that you will see in a few slides. So this is a microscopic non-reciprocal force exchange. And I want to emphasize that this is not specific to starfish. Generically, any spinning object can actually generate a non-equilibrium object can generate such type of force and torque exchange in the system. So this is the example of the two-body and three-body videos. And again, you can see that you can see that the two-body and also three-body and so on and so forth actually starts breaking chiral symmetry and they rotate. Now I'm going to briefly focus on the properties of the crystal's ground state. And one of the features is that they nucleate and grow and dissolve naturally as the embryo progresses through the development. And what we see is that a crystalline order initially increases during the growth phase, whereas the dissolution is preceded by a loss of orientational, translational, and dynamic order. So I'm going to just show you one type of order, which is the orientational order. And we can do that by looking at the local bond orientational parameter, this size 6. This is done in the co-rotating frame. And the magnitude of this size 6 is quantifying the local hexagonal order, and the phase angle is basically indicating the local bond orientation. And the videos that you see here is the experimental measurements of the order parameter evolution. Now, these videos may be a bit fast, so let me just show you histograms of how this order, order, and disorder develops in the system. So initially, because we have multiple crystal nuclei that come together, we can see that we initially have a lot of defects within the system, in particular grain boundaries. So this results in a broad distribution of the magnitude and the phase of size 6. But because these crystals, this polycrystallite structure, the domains are rotating with respect to each other, you end up getting this large, nearly defect-free crystal. And then at the end, what happens is that we have noise that's being introduced in the system, either because of the shape of the particles, the fluid flow, and that eventually leads to order-disorder transition, and then finally dissolution of these crystals. Now, this was focusing on how the ground state looks like, but we were interested in understanding what the excitation looks like in a system like this. And in particular, because this is a system that we are breaking parity by spinning the material constituents. And we, as I mentioned, we have transverse force and torque exchange in the system. So again, I want to remind you that we have a global rotation of the crystal because of the rotation of individual embryos. But we observed something more striking if when we looked at the co-rotating frame of the cluster. And what you see is that the crystal is supporting self-sustained chiral waves and shear cycles. And this is a video that you can see an example of this type of oscillations. And what I want you to note is the time scales here. This is an overdamped system, but you can see these are waves that can persist for very long times. And of course, this highlights the non-equilibrium nature of the system. Maybe to better visualize this, I'm going to show you the displacement fields, both in terms of the magnitude as well as the angle. And you can now clearly observe the propagation of these self-excited displacement waves that going through the entire body of the crystal. And again, I want to emphasize that this is a fluid-embedded crystal lattice, so it's overdamped, and the existence of such waves should come as a total surprise. Okay, so let's see why this is an unusual discovery. So just briefly, if you recall standard elasticity from Landau-Lifshitz, we know that we derived the entries of the stiffness tensor under a variety of assumptions. And energy conservation is one of the important requirements, which actually has striking consequences. And in the case where we have a two-dimensional isotropic media, it constrains the stiffness tensor to only two independent diagonal entries, bulk and the shear moduli, which you can see these two diagonal components. And in 2020, there was a beautiful work from Vincenzo Vitelli and co-workers, including Anton, who's also local, came out where they showed that if we waive this standard requirement of energy conservation in linear elasticity, one can unravel unexpected mechanical behavior. And in particular, what we see is that entirely new elastic moduli appear in stiffness tensor. And these are off diagonal and odd, and hence they term this odd elasticity. And again, to re-emphasize, these odd couplings are generically expected when the constraints of equilibrium are lifted. Now, odd elasticity is a macroscopic non-reciprocity of the response of the system, and it arises because of the microscopic non-reciprocal interactions that we have in this system. And the existence of oscillatory motion in response to specific stimuli is one of the predictions of the theory. And this is because these waves can be self-sustained, because in this system, activity provides the energy to overcome dissipation in each wave cycle. Now, to visualize this oscillation waves in our system, we can determine the displacement gradient tensor and extract the four principal strain components, which is divergence, curl, shear 1, and shear 2. And what's plotted here is basically the magnitude of these four principal components around the boundary of the crystal. And this is plotted as a function of time. So this is what the typical kymograph. And you can see this sustained periods of oscillation. Now, what's more interesting is that if you look at the two-dimensional phase space trajectory of two of these components, for instance, shear 1 and shear 2, what we see is that it traces out a closed ellipse. And this ellipse is indicating the emergence of an autonomous self-sustaining elastic engine cycle in which the system is converting internal energy into mechanical work to offset this dissipative losses. And again, the area that's embedded by these curves is the work that's done on the environment. And this is something that I find absolutely remarkable, because this is a system where we are linking rigid body mechanics to thermodynamics. And this is, of course, similarly the case if you look at divergence and curl. And we can quantify the lower bound of the work that's associated with these strain cycles. This is another part of my group where we're interested in understanding how we can quantify work and bounds on energy dissipation using statistical and information theory metrics. So what we can do is we can look at the statistical irreversibility of the observed cycles, and we can then compute the lower bound on the amount of irreversibility, or the lower bound on the amount of dissipation in the system. And the heat maps that you can see here is basically giving you an idea of how the system, when it's excited, is actually dissipating, is doing work on the environment. These cycles have a direction as well, so I'm going to just skip that part, but the direction of these cycles is actually telling you that the work is being done, and it's consistent with the signs of the odd moduli that you get in the system. I'm going to briefly mention that so far, everything I told you is about elastodynamics, which points towards the existence of odd elasticity. But the question we wanted to ask was whether we can extract these odd elastic coefficients. So what we did is we started looking into elastostatics by taking advantage of the fact that this system can have defects, lattice defects. And this is examples of the defects you get in the system. You can have defects where you can have a misaligned embryo, so it's sitting on its side, and this introduces a 7-fold coordination defect. And you can also have instances where an embryo is departing or missing, and that's a 5-fold coordinated vacancy defect. You can also have edge dislocation. So these are bound pairs of 5- and 7-fold coordinated embryos. And what we can do is very briefly look at the associated displacement and strain field around the defect. And again, work by Vincenzo's group and co-workers, they have shown that this strain field contains information about the effective mechanical properties. So I won't go into technical details, but we can parameterize the strain field using 2 angles. One is an orientation angle, and this is done with respect to the Berger's vector for those of you who are interested in crystallography, and then also a shear angle. And in a generic isotropic elastic solid, linear elastic solid, there is actually a relationship between these 2 angles. Basically alpha is parameter free, and this is shown here in dashed lines, so you have these singularities. But when we looked at the measured values of alpha in our system, we actually see this more complex pattern that can only be explained by allowing for a more exotic material response that actually includes this non-vanishing odd moduli. And then with this additional delta alpha, we can measure the ratios of odd elastic moduli in the system. And again, the presence of those globally rotates the local axis of shear deformation by a small angle delta alpha. Okay, now everything I told you was this, that we have a system, it's exhibiting unusual non-reciprocal properties all the way from microscopic to macroscopic, but it turns out that there is actually some new faces to this living chiral crystal. In particular, we were when we were looking at how we can excite this type of oscillations in the system, what we observed was that in addition to getting transient odd oscillations, we can actually get spontaneous excitation of collective velocity oscillations that initially grows in time and persists over several oscillation cycles before decaying and restoring to its non-oscillatory state. So basically, in contrast to the odd oscillations where we have transient dynamics, these oscillations actually correspond to a stable state that can persist for even longer times with constant amplitude. And the way to look at this is that let's look at basically a slab of this crystal, and then look at the velocity vector averaged over the field of view and span it by its two components, v of x and vy. And this is what we have plotted here. You can clearly see, first of all, we have this kind of random type fluctuations, but then the system suddenly starts exhibiting this stable oscillatory state, and this static this oscillatory state actually is constant amplitude and can persist for very long times. And then on the system then relaxes back to its static state, which is basically just fluctuations around a zero mean velocity. Now, if we look at the global temporal dynamics, we can also try to see the spatially resolved dynamics of the velocity field. And again, what we saw was that this oscillating region initially grows in space, and then it stabilizes at a constant area during stable oscillations, and then contracts in space as the velocity amplitude decays before vanishing altogether in the static state. So this is kind of like demonstrated in basically having two states, a quiescent state or a static state and an oscillatory state. Now, to understand this bistability between static and oscillatory state, we kind of started thinking about the fact that despite the fact that living chiral crystal is effectively a two-dimensional solid, the embryos that is composed, the embryos that compose the crystal are three-dimensional objects. And in particular, I want to bring this video back where you can see that the embryos, as well as those that are individual, but also within crystal, they can tilt away from the normal to their air-water interface by an angle theta. And what happens is that now the AP axis can potentially precess about the normal axis. And what we kind of hypothesized was that the static state corresponds to the upright embryos with theta 0, whereas the oscillatory state would be corresponding to a stable finite tilt angle, which we call theta naught. Now we can kind of expand the equations, that coarse-grained equations that describe the system. So we can, of course, have the equations that describe the displacement field, where we have the usual elastic modulus tensor containing both the conventional and the odd elastic moduli normalized by the friction coefficient. But then the combined effect of the finite tilt and precision is to basically endow embryos with an orientation-dependent self-propulsion, which is characterized by a constant velocity, which we call V naught. Now, we have two additional fields. One is going to be the orientational theta, so that's going to be the tilt angle dynamics, and then the other field is going to be the phi, or the azimuthal orientation dynamics. And if you look at the phi equation, you can see that we have two moments of inertia. One is IAP, which is the moment inertia about the AP axis, and the other one, I perpendicular, is any of the two symmetry axes perpendicular to the AP axis. Now, finally, we have a phenomenological equation that describes the dynamics of theta. And what it basically is telling us is that the local relaxation of the tilt angle to a stable value as theta has two stable values, one theta 0 and one theta naught. And we basically have a theta c, which is the unstable tilt angle that separates these two stable angles. And then you see two constants here. One is d, which is and the other one beta, which is the strength of tilt and tilt displacement coupling in the system like this. Now, what this means is that we have something that is in essence very similar to an expanding theta population, meaning that in regions with large theta, we can have instances where it can invade a region of low tilt via an expansion of a tilt wave, and which then would appear as an increase in the area of oscillating region. And likewise, depending on the parameters, we can have a high tilt state that can become more unfavorable, and the oscillation region shrinks until we are left with a uniformly static state. Now, we can construct this theoretical phase diagram, which basically delineates the parameter regime in which stable oscillations cannot occur. Now, what I'm going to briefly mention is that there are several predictions that can be tested in our experiments, and I'm going to show you a couple of examples of that. One is that the average tilt angle of the embryos in the oscillatory state should be larger than the average tilt angle in the static state, and this is indeed what we observe in our experiment when we look at the static state and the oscillating state. And then the next prediction is that the embryo rotation frequency is directly proportional to the divergence of the displacement field. And because the divergence is oscillating in the oscillatory state, the theory predicts that the average rotation frequency of the embryos must oscillate in phase with the divergence, which indeed is also another prediction which we can experimentally verify. Now, everything we did so far is basically looking at spontaneous oscillations. The next question was whether we can actually induce this transition from one state to the other state. And in particular, we wanted to see whether we can excite the oscillatory state from the static state using external perturbations. And to do this, basically, we performed a series of experiments in which we apply a controlled mechanical perturbation to the system. So we confined the chiral crystal in a C-shaped chamber, and the fourth wall of the chamber is a piston that's attached to a syringe pump, and we can control the piston velocity and therefore performing a uniaxial step compression experiment over a wide range of compression rates. And indeed, what we observed was that we can induce sustained oscillations mechanically starting from the static state. And in fact, it's a Goldilocks situation, meaning that the probability of excitation of oscillations depends on the compression rate. And the way we understand this very briefly is as follows. When we have a low compression rate, we are basically exciting long wavelengths or low wave vector deformations, whereas the high compression rates only leads to local plastic deformations or high Q deformations. And in fact, our theory predicts that if we look at the Fourier spectrum of the initial displacement in the system, this Fourier transform spectrum is dominated by a band of wave vectors whose mean is directly proportional to this compression rate. So this is something it's a new observation for us. We are very excited about, and we're trying to explore this in many directions, in particular its connection and its with odd elasticity, because if you think about it, the system is actually exhibiting two types of elasticity. One is odd elasticity, but the other one is a form of active gyral elasticity. Now, to actually do this, we have been on quest for getting the dispersion relation in this system. And this is something that has now become a reality for us. It's just very new results, which we've been working on with Jorn Donkel's group for a while. But now I can show you at least the first example of that. So where you can see that this is a dispersion relation for the system. And you can see we have both acoustic transfer and longitudinal modes, which show this quadratic feature. But then we also have this optical flat band, which kind of like corresponds to the fact that we have this type of active gyroelasticity in the system. And in fact, there's a very cool feature, which I'm really, really excited about, and I hope to talk more and show you results, hopefully, in another setting, where the system it admits a non-trivial coupling between odd elasticity and gyroelasticity, which actually what the theory predicts is a resonant interaction between the second harmonics of, if you look at omega and also odd elastic vibrations. And in fact, we can see this type of couplings, and again, just very, very new results. I'm hoping to be able to show that very soon. Now, what I want to kind of like wrap up this part is the fact that these structures where they support this type of chiral waves, they exemplify this upward energy transport from individual microscopic constituent to the macro scale. And for us, it's really an incredible sandbox or playground to try to really understand this upward energy cascading in a system or in any type of active matter system. And this is something that we are trying to actively explore. Now, do I still have time? So I can maybe briefly mention two other points. Okay, I don't hear any complaints. So I'm going to just maybe continue. I'm going to show you two other things that we can do. First, again, related to this living chiral crystal. And everything I showed you so far is looking at crystals with identical particles, because we start the experiment with embryos that are at the same developmental stage. But you can imagine the phase space to explore is actually immense. And this is a new direction that we have been exploring, namely to try to look at what happens when we combine particles from different developmental stages. And in particular, what basically we are doing is we are mixing particles. Yeah, that's perfect. Yes, yeah. Yes. So we can start playing this game of actually mixing particles of different developmental stage. And then we actually can see, and effectively what we are doing is we are tuning the non-reciprocal interactions between the particles within the system. And we can see many examples of new phases that emerge. We can have phase coexistence. So this is an example that you can see here. But we can also see chiral flocking. And for instance, this is an example of where we can see chiral flocking and then a transition to the crystal at the end. And the way we actually understand this is basically under the umbrella of non-reciprocal phase transitions, where we actually have order parameters that oscillate. And then here in this particular case, we have non-reciprocity between structure and dynamics in the system. And again, I'm happy to answer questions about this maybe during the talks, but then we can actually, again, this is an incredible phase space to explore. So, and then lastly, I promised I'll show a sea urchin as well. The particles that, so the periodic table that we have is actually very large. And one example is sea urchin, where now not only they initially have the same features as starfish, but they actually also start breaking shape symmetry. So this is an example where they go from being something that's very similar to starfish to actually become a triangular type structure. And there you can see that chirality, for instance, if you look at the polar field, you can see that now chirality is actually an emergent phenomena in the system. And this is, again, something that we are very excited to explore. And this is something that we're theoretically exploring with Farzan Wafa, who's also in the audience. And yeah, you can even go further and then observe this unusual shapes. So with that, I'm going to just quickly mention that this is the work of an incredible group of former members and current members, and my collaborators, in particular, Jorn Dankel and his group. And I'm happy to take questions. Sure. Yeah, that's a wonderful question. I always get that question. So I guess I can always show this image. So the starfish we're looking at is, I mean, of course, in general, starfish echinoderms are broadcast spawners, and this type of starfish lives in the intertidal zones, where you have shallow waters that can kind of actually fluctuate in terms of temperature, acidity, and pH, everything that you can imagine. So in practice, it's possible that this could form in nature as well. And in fact, a couple of months ago, there was a very nice paper, which we're trying to also now look in that direction. What they showed was that when these embryos are together, they actually have a higher survival chance. So basically, it's an Ali effect. When they stick together, they have a higher chance of survival. They also showed that you can get calcium waves propagating through between these embryos. So this is a new direction in the group. So we're trying to see, actually, you do have this type of communication between them, which again adds a new face to the whole story. So I hope to be able to answer that question definitively, maybe soon. Hi, Mike. Thank you. Mm-hmm. Right. So yes, yeah, it's I guess it's not yeah. So I think that's an interesting question. I mean, the reason for it is that it's basically, if you look at kind of like again, like I can show the videos, but if you look at the dynamics, you can see that they have this precision dynamic. So you get this kind of I mean, torque-free precision in the system, which basically comes from the fact that, again, they can tilt and then they can precess as they tilt. So this is kind of like where this idea comes from. So I don't know if that entirely answers your question, but this is kind of like you can clearly see this type of dynamics happening in this. Sure. Right. And yeah, absolutely. And right. And it probably has, again, like I think I briefly mentioned that it's kind of like an active form of gyroelasticity. It's not really gyroelasticity, but it's an act. Again, we have them because of the fact that we have activity in the system. So yeah, so maybe there is a better way to interpret them. I agree. Yes. Yes. Right. So the Reynolds number are small. So they actually have like their velocity is about zero point 0.1 millimeter per second. So that low Reynolds number came into account where we were looking at kind of like the Stokes-Lit analysis of like the system. So I mean, if you want to scale this up to what happens, like I would say like maybe an example that would be maybe more relevant to this is if you look at again gyroelasticity, or basically when you have the systems that William Irvine's group working on. So there in the limit where actually in the overdamped limit, the gyroelasticity becomes odd elasticity. But here there are two different things. So you have the linear elasticity, and then you have this additional kind of precision, which is basically again, it's an active, maybe there's a better way to call it. It's an active form of this precision, and that's kind of like where you get the dynamics like this. So I don't know if that entirely answers your question, but I think Vincenzo's group probably has looked at that definitely, for example, and then maybe William's group as maybe the closest I can think of. Of our system, you're saying, or just like basically spinners with this type of interactions. Right. Sorry, was that the question, or sorry, I didn't get that. Yes. Right. I mean, in this system, I think if you go to high Reynolds, I mean, if you have, for instance, also, even if you do a small perturbation, the crystal breaks, right? So this is really looking at kind of like water-air interface that's not disturbed by like any external perturbation. I think if you go to high Reynolds number, you probably can get similar behavior, but I'm gonna just I don't know, like I'm gonna leave it at that. But this is for low Reynolds number, but with an active form of this torque-free precision. So this is basically, I guess the way we think about it is that when, like, if you imagine you have one of these embryos, so they're kind of like, they're basically rotating, and then that's when you kind of like, you get the global kind of rotation happening. Now, when you basically, I guess what we don't really need to fine tune that to be able to get like the type of oscillations that we get. I guess if that's your question. And I mean, maybe I think it's actually like something I can show you is like the theory predicts that when you kind of like look at you are at the oscillation phase, you actually have this coupling between the rotation frequency and the divergence. And indeed, this is a video of showing that. So you can see that, like hopefully in a minute, you can see that so this is the oscillations happening, and then you can clearly see that we actually get oscillations in also like in the divergence and the rotation frequency. So that's yeah, I guess so. Yeah, I guess this is this is actually so you're talking about the tilt displacement coupling. So this is actually like it's small coupling. Beta will be small values.